Hello everyone, welcome back to term 3 of SPAAM. We have a very exciting set of talks for you today for the first week of term. First we'll be hearing from Jack Buckingham from MathSys talking about searching over functions, Bayesian optimization for two-stage problems. Take it away, Jack.
Thank you. Yeah, so my aims are twofold, I guess. I would like to tell you what Bayesian optimization is and give you a general recipe to how to come up with these acquisition functions that you will know what they are at the end of the talk. And then to give this application to two-stage problems, which are one version of a search over a function space. So two-stage stochastic programming was first studied in operations research in the 50s, and then later rediscovered sort of in engineering under this name of active robustness. And it's the design of products that have a fixed aspect of their design that you can't change, and you pick once in the face of some uncertainty, and then you reveal something uncertain, and then you've got this active part that can respond to that uncertain environment. So as a concrete example, the wind turbine here, an engineer has to design the shape of the turbine blade once, and it has to work in all the different wind conditions, but then they can change the pitch of the turbine blade later to reduce the load in stronger winds. And another example is an optical table, where physicists want to run experiments on the top of the table. They want no vibrations, basically, otherwise they get dodgy results. And so you want the table to reduce the amount of vibration that's coming through from the floor. There are some springs in the legs, so you can build it once with certain components like that that have to be fixed. And then you've got active damping, maybe, that can respond to, say, the frequency of the vibrations. Classic approaches in operations research will assume that you maybe have a fast function that you are trying to optimize. So maybe it's given by a formula, you know a lot about it. You can compute gradients from it. You can throw gradient descent methods at it. It's convex, perhaps, because a lot of optimization works based on things being convex. But in the engineering problems, you've just got a simulation, and it's like a black box. You know a lot of what went in, but it's so complicated you can't do this extra analysis. The simulations tend to be slow. If it's a fluid simulation or a finite element analysis, it can take hours to run. So you don't really want to have to run that many. They don't give you a gradient. So if you want a gradient, you have to do numerical gradients, which is even slower, even more evaluations. And they tend not to be convex as well. So they've got lots of local optima. And if you want to find all of them in order to find the best one, you have to do multiple starts, which is even more evaluations. So you need a new tool to solve this sort of problem. And that tool is going to be Bayesian optimization. So there's 3 sections in the talk. The first one, we're going to say, what is Bayesian optimization? What's the general framework? What principles does it work on? Then we're going to say, okay, there's this thing called acquisition functions that you'll then know what they are. How do you design them? And finally, the application to two-stage problems. So traditional approaches, probably the simplest possible way of solving a problem like this, where you can only evaluate single simulations, is a grid search. And this is quite popular in hyperparameter tuning problems, where you say, okay, in this 2-dimensional example, split each axis into a set number of points, and then draw a grid and evaluate every one of these dots, and then pick the best one. It's quite simple. It works reasonably well. Yeah, you miss bits in between, but generally you still find a good enough result. However, it's really slow because you have to evaluate all of these points, and as your dimension increases, the number of points in your grid increases exponentially. So people get around this exponential growth problem by saying, okay, instead of forcing ourselves to have a grid, we can sample randomly. So that's what's happening in this example, where we scatter points randomly over the space. We're not forced to have an exponentially growing number of points. We sacrifice some quality of the solution, but at least we have a method of doing some sort of search. But it's not too efficient because you have these clusters appearing in a few different places. And yeah, that's because the points are sampled independently. So the third approach is to say, okay, don't sample them independently, sample them in some sense jointly. And there are these low discrepancy sequences, such as the circle sequence, that will force your points to be spread out. And they sort of generate points sequentially in sort of batches of powers of 2 in this example. And you get pictures like that. But if, say, this point came out really bad and that point came out really bad, then why would you keep looking around this area? You're kind of wasting a lot of your effort, because none of these actually look at what values you're getting back from your simulation. So the idea of Bayesian optimization is to account for the fact that maybe you've observed some bad values here, so don't look there anymore. You want to focus on the areas where you know are good and the areas where you know you don't know, so where you haven't looked yet. We need a model, therefore, to capture what do we know, what don't we know, and that's going to be a Gaussian process. So if we step back, I've given a previous talk to sort of show how you might construct a Gaussian process, but for this talk, think random function, so random variable, and then generalize it to random vector, and then if you take the dimensions to infinity, you basically end up with a random function. It's nice because just like when you condition a multivariate normal, you can also condition a Gaussian process, and you still get a Gaussian process. It remains Gaussian. And the mean and covariance functions of this Gaussian process can be computed with linear algebra, i.e. it's easy. So it's a very tractable model, and that's why people like it. And as an intuition on the right, I've drawn here, say, the mean of a Gaussian process that's been conditioned on 4 observations and a 95% confidence interval around it. And another way of looking at it is to draw samples of the model. So how do we use this model then in Bayesian optimization? It works in sort of 5 steps. You start off by collecting some initial observations. So maybe that's with the Sobel sequence, but it's a very few number of observations. And then you fit a Gaussian process to it. So fit here means there are some parameters in the GP, such as how wiggly it is, so the length scale that you have to fit. But that you model it with the Gaussian process, and then you want to come up with this thing called an acquisition function. And that's going to tell you, okay, I need to make this exploration-exploitation trade-off. This bit's good, this bit's bad, this bit's unknown. Where should I sample? And so it scores every possible input, and then you want to choose the input with the best score. So you keep repeating this, model it, choose where to sample next, run the simulation, model it, choose where to sample next, run the simulation, and eventually you'll give a recommendation. So how do we actually come up with these acquisition functions? The approach I want to talk today about is these sort of greedy one-step based optimal approaches. So you write down something that you care about, some sort of metric of how good you're doing, and then you choose the next observation to make that metric improve as much as possible. So in it, the most widely used one is called expected improvement. So if I've observed x1 to xn so far, then the answer I'm going to recommend at the end is this xn star, which is the best of the ones I've observed so far. And what we want to do is we say, okay, we want the best one to be the best, basically. We want to improve it the most each time, the score of that best one to be the best. And so if either, when we make a new observation at little x, we either get a better answer, and then we can return that one to the user, or we keep the old one. If we do worse, we keep the old one, we can still return that. So the score is somehow the maximum of the f of xn star that we've got now, and f of x that we've got in the future. So here, the best value after the next observation is the maximum of the current best and the one we might observe. And then we subtract the best so far now, so it's an improvement. How much have we improved? If this is lower, it's 0. If it's higher, then we've improved. And then we take expectation, because this value is random. We don't actually know what we're going to observe. We have to use the model. And this is expected improvement. And then graphically, over here, if I'm going to evaluate it at this orange line, then the best so far is where that horizontal line goes through, and anything above that is better. So we're integrating the value of the observation multiplied by an indicator for I above the line. So it's that shaded region there. It works well in practice. I think I said it's probably the most popular acquisition function in practice. It's got an analytical formula here that you don't need to worry about too much, apart from the fact that it's fast. Basically, it gives results really fast. But you do need full observations. So I mean by this that these two-stage problems that we talked about at the beginning, we want to optimize the expectation over these uncertain environmental parameters, and we never actually observe that expectation. We only observe simulations at specific environmental parameters. So we can't apply expected improvement out of the box. So the thing we do to change that is we still have observations 1 to n, but then instead of recommending the best one we've seen so far, because we haven't seen a full observation, we use the model. So we recommend the one that's got the best posterior mean of our model. And then if you do exactly the same thing as expected improvement, you get what's called knowledge gradient. So you've got xn plus 1 star is the value, the best value after your next observation. You can score it with your model f, and then you subtract the best so far at the moment, and then because this f is random on both of these, and xn plus 1 star is random, you take expectation. And graphically, here, if we're observing at this orange line here, maybe we observe this point here, then the best so far is the maximum of the blue line. The best so far after this next observation is that green star. And that, in this example, is improved. It doesn't always improve, but when you take expectation, over what you might observe over the orange dot, then it will be a positive quantity. And that difference in expectation is the knowledge gradient. And again, that gives you the knowledge gradient at this point, and then you can use a gradient-based optimizer to find out what the best value is, and therefore where you should sample. So it's a natural extension of expected improvement that works in our setting, so it can handle these partial observations that we have with the two-stage problems, but it doesn't have this nice analytical formula. It requires some approximations, and after those approximations is relatively a lot slower to optimize, so maybe 20 seconds to optimize instead of sub-second. In these hour-long simulations, that's still not a problem, but it's worth factoring in because some applications it's a lot faster simulations. So a third example of one of these things is to say, okay, suppose rather than caring about the score of the value we recommend in expectation, suppose instead we consider what's the probability distribution of where the maximum is. So this red line here is showing us what the probability of each point being the maximum is. And then this distribution has an entropy. So entropy is a measure of uncertainty. And if we're more certain about where the optimum is, that's better. And so the idea is to say, okay, choose the next sample to reduce the entropy in this distribution of where the maximum might be as much as possible. So if we were to observe on that orange line, if we observe the little dot there, that's below the mean. It's kind of worse than we expected, and so it's going to shift this distribution to the left. We've learned something, so it gets narrower, and its entropy's gone down. And then using those calculations, you can say, okay, well, where is the point that gives us the biggest reduction in entropy? And so then in formula, you've got the current entropy minus the entropy after your next observation, and again, you're taking expectation over what that next observation is. So it's a different way of doing it, but it still works well in practice. It can handle these partial and noisy observations, and it, like knowledge gradient, though, requires a lot of approximations, and it is similarly slow when you're trying to compute it in practice. Okay, so in the last 5 or so minutes, I want to talk about how we've applied knowledge gradient, which was the middle one of those 3 acquisition functions, to the two-stage problems. So I gave you sort of the practical setup at the beginning, but in terms of equations, we've got some function f that is a simulation, expensive simulation. We have some design parameters x that are the fixed design, so the shape of the turbine blade or the spring constants in the springs of the optical table. We have some uncertain variable u that is maybe the frequency of the vibrations of the floor in the optical table example, and then we're looking for this control function g that maps frequencies to the damping parameter in the optical table. So these adjustable variables y equals g of u. So we choose x, then we see what u is, then we choose a y that can depend on that u, and we want to maximize over both of these things. In pictures, here I've plotted the environmental variable on the horizontal axis and the adjustable variable on the y-axis. Yeah, I guess it is y, so it's okay, but I'm trying to avoid using x and y when x means something. We're looking for this blue line that's going through all of the highest points. So lighter is better, and the blue line is the optimal control going through all of these points. And we not only want that optimal control, but we also want the best of these 3 fixed designs that I've drawn here. Obviously, in practice, there's a continuum, but you can only draw so much on one slide. In this example, this one's the best, I think, because it's generally going through all the lightest areas. You can see visually. And what can we do? This is just a reminder, we can run simulations at a specific environment. So we can pick an x, we can pick an environmental variable u, and we can pick this adjustable parameter y. So we can pick the wind turbine shape, the wind conditions, and what pitch we put it at. And then we run the simulation. Maybe we get a noisy observation if it's a stochastic simulation. If it's not, then forget the noise. But the point is these simulations are expensive, and it's this sort of partial observation thing. You don't get to observe all the u's at once. When we compare, I'm just going to compare to a couple of algorithms. One is a simple random sampling algorithm. So if you remember the Sobel sampling before, then you can say, okay, these come in a sequence. If you keep sampling, it's like a random search where it's really spread out. So this gives us one way of comparing. And the second one is these 2-step problems. So we talked to an industry partner about how you solve this sort of problem currently, and they say, okay, well, you can sort of design the wind turbine shape, and then optimize a control policy to go with it, and then switch it around and say, okay, keep that control policy, now improve the design, and then switch it around again and keep repeating these steps. But in practice, they can't repeat them very much at all because it's a really expensive process. It takes a lot of time. And this, obviously, yeah, what you see, it doesn't perform as well. So in the optical table example, here is a schematic diagram of that table. It's got two springs with the spring constants that are the fixed design. It's got the damper in the middle that can respond to the floor vibration frequencies, and we're trying to minimize the amplitude of the vibrations on the table surface. And here we're plotting regret, so the difference between the expected difference between what you get and what you could get as the optimization progresses. So as you collect more evaluations, the blue line is converging fastest. So that is the knowledge gradient approach from earlier in the presentation, and it's converging a lot faster than this random approach, and a lot faster than the two-stage one in green. As another example, I didn't mention this before, but the supply chain problems are similar. You have maybe you've got a pharmaceutical process and you're trying to make some sort of pharmaceutical thing, and it's got some chemical inputs, and some of them you can have quite a short lead time, so you can have quite a good idea of what your demand is when you order them, but others of them have a really long lead time, so you really don't know what the demand's going to be when you make this decision. So you have this two-stage problem where you have to make some decisions up front with a lot of uncertainty, then you learn about the demand more, then you can order these other products later. And your aim is to minimize costs. And basically, again, the solid blue line here is the knowledge gradient policy from earlier in the talk, and the orange one is again random. And these horizontal lines are the state-of-the-art algorithm that was applied previously to this problem. And you can see that even after 2,000 evaluations, they've got to this dotted line, and we've overtaken that line at 100 and something. So that's good. And the story is even better because in this paper, they actually assume that you only need to pick the upfront quantities now, and then afterwards you can have some oracle that tells you what the best adjustable variables are. And if we do that in our one, then obviously we don't need to use the G we optimize. We can just use we could just say what's the best function G for that X, and it can do even better basically. So it's a big improvement on the current state of the art on a real problem. And the benefit mainly, you can see that the random algorithms also improve on this, and the benefit is mainly coming from the fact that we model the space jointly over all of it, so all the observations we've observed so far we can make use of, whereas in this other paper they end up segregating the design space. So for any given fixed design, you can't share observations between fixed designs on the inner optimization level. It's a nested optimization. Okay, so in summary, Bayesian optimization is a good way of optimizing expensive black box functions, and not just simple problems, but also such as this two-stage problem. One-step Bayes optimal acquisition functions are a good way of greedily designing greedy acquisition functions. It's a good trade-off between being efficient and getting good results. And knowledge gradient works well for two-stage stochastic programs, as was demonstrated in the last two examples. So thank you very much.